Hello, welcome back to Mech 416/816 Engineering Acoustics. In this video, we are going to go through standing waves for the linear acoustic wave equation. So just like for elastic media, we can apply this technique of separation of variables to the linear acoustic wave equation. So for the 3D acoustic wave equation, we can write that the pressure P of x comma t is equal to, and here x is a vector, so it's going to be equal to a function big T of time times a big X of little x times a big Y of little y times a big Z, which is now a function of little z. We can then substitute that into the linear acoustic wave equation and then end up separating the variables just like we did for elastic media. We'll get c squared times big T double dot divided by big T is equal to big X double prime over big X plus Y, big Y double prime over big Y plus big Z double prime over big Z. And so on the left-hand side, we have a function of time. On the right, we have a function of three spatial variables. And as a result, because these are functions of different variables, they can only be equal to a constant, and we're going to call that equal to minus lambda 1 squared. And then from there, we're going to get the following equations. We're going to get that T double dot plus, in fact, you know what, instead of using lambda 1, let's just go ahead and use omega here. So we're going to get minus omega squared, and we'll just save ourselves some time here. So we will then write T double dot plus the quantity C times omega that quantity squared, or we can just write C squared omega squared big T is equal to 0. That's our first equation. And then dealing with the right-hand side, we will get that omega squared plus big X double prime over big X is equal to minus the quantity Y double prime over big Y plus big Z. Let me rewrite that. Big Z double prime over big Z. And now we've got a function on the left, which is a function of x. On the right, we have a function of y and z. And so again, these must be equal to a constant. We will call this minus lambda 1 squared here. From here, what we're going to get is that big X double prime plus the quantity omega squared plus lambda 1 squared, all of that multiplied by big X is equal to 0, and we're going to simplify that and say that x double prime plus k1 squared times big X is equal to 0, where of course now k1 squared is equal to omega squared plus lambda 1 squared, and we're going to just deal with k's instead of lambdas. Okay, so now let's deal with the right-hand side of this equation. So we get that minus y double prime over y minus big Z double prime over big Z is equal to minus lambda 1 squared. So what we're going to do is we are going to bring the Z over, and so we'll get Z double prime over big Z is now equal to lambda 1 squared minus y double prime over big Y. And again, now we have on the left a function of z only, and on the right a function of y only, actually. And so we can call this equal to minus k3 squared. And then from here, we're going to get that z, well, let's deal with the y. First, we'll get that y double prime over y is equal to lambda 1 squared plus k3 squared, which we can say is equal to k2 squared. So lambda 1 squared plus k3 squared is equal to k2 squared. And therefore we get that y double prime plus k2 squared y is equal to 0. And then lastly, for the last equation, we get that z double prime plus k3 squared, big Z, is equal to 0. And so we ended up now with 4 ordinary differential equations. First, we have t double dot plus c squared omega squared big T is equal to 0. Then x double prime plus x, actually it should be x double prime plus k1 squared big X equals to 0. Then y double prime plus k2 squared big Y equal to 0. And then z double prime plus k3 squared times big Z equal to 0. Those are our 4 ODEs that we now have. Or if you want, you could write this as xi double prime plus ki squared xi equal to 0, for xi being equal to big Xi, which is a function of x, little xi. True for I equals 1, 2, and 3. Not extending to infinity, ending at 3. So now we have a set of 4 second order ODEs that we can solve similarly to what we did with the elastic wave equation. And what we'll find here is that xi of xi is equal to some infinite sum from n equals 0 or n equals 1, depending on the boundary conditions, where we'll get a sub in times the cosine of k sub in times xi plus b, and that summation acts across all of this, b sub in times the sine of k sub in times xi, where a, in, b sub in, and k sub in are determined by the boundary conditions and the orthonormalization. So what you'll do when you actually apply this is you'll use the boundary conditions to eliminate 3 of the a's or 3 of the b's, depending on what the boundary conditions are. And then you'll use the other boundary condition to find what k is, and then you'll be left with an arbitrary constant in each direction, which you would normally determine by orthonormalization, which we are not going to cover in this class. Okay, that covers everything that I wanted to say for standing waves. We will do a worksheet on this, particularly looking at spherical waves. Sorry, cylindrical waves. We'll do a worksheet for cylindrical waves. And with that, I'll say thank you, and you're